This is our 3D printer. Oh, sorry. Let me move this out the way. This is our 3D printer.
Tell us a little bit about yourself.
My name is Alex Losada, and I am a student, mechanical engineering student at UCF, completing my last semester.
Why did you fund this project?
So I decided to propose and fund this 3D printer project because actually of my background as a machinist. So I've been a machinist for about 10 years, and in my experience, my desire for features in a machine tool product is that it be fast and accurate and reliable. Last year, I started doing an honors undergraduate thesis in additive manufacturing, and that was kind of my first foray into that type of manufacturing. And what I found among the products, among the 3D printers that I was looking at, was that they typically lacked at least one area that I find to be kind of important in a machine tool. So when you look at a product, say like an Ultimaker, which for most people is pretty expensive, they're kind of small and they're slow and they're limited in their capabilities as far as what they can print. So what I wanted to do was to create a printer that was fast and accurate and large and had capability of printing with materials that could go directly into service, all while keeping kind of a low price point and lowering the barrier of entry into additive manufacturing.
Hi, my name is Mina To. I'm a senior in mechanical engineering, and I was the project lead.
Hi, I'm Emily Dimboski. I'm a senior mechanical engineering major, and my part on this project was the thermal management and the thermal components.
Hi, my name is Kriya Mistry. I'm a senior at UCF studying mechanical engineering. I worked on the thermals and manufacturing in this project.
Hi, my name is Derek Haas. I'm a mechanical engineering major, and on the project I was responsible for simulations and controls.
Hi. Hello, I'm Jason Rock. I'm a senior in the mechanical engineering program at UCF, and I designed and helped build the electronics for the large format 3D printer.
The goal of this project is to develop a large format 3D printer that is capable of printing with high performance engineering plastics at a high print speed and at a maximized print bed size. Our printer shall have a build volume of 2 feet by 2 feet by 2 feet at a max print speed of 1200 inches per minute, all while minimizing cost as much as possible. There is now a huge gap between industrial printers and hobbyist printers. The market for a printer having qualities such as high print speed, large build volume, and low cost is almost non-existent, as printers with these qualities are typically within the range of $10,000 to $150,000. All printers have pros and cons. To create a 3D printer that has the design qualities of high-end 3D printers, all while minimizing costs, is one of the purposes of our project.
So one unique aspect about our project is that we chose to manufacture all of our own parts in-house in my shop. Each part required a great deal of attention because the tolerances are critical, and some of them were even down into like a 1/1000th of an inch range. So the process involved programming the G-code for the part and then setting up the tools in the machine and then making sure that we set all the correct work offsets in the machine. And then because each part that we were running was the first time we run it, we have to actually prove out the CNC program, which is a process that involves watching the program run for the first time and making sure that it's doing what we want it to do.
When designing our 3D printer motion system, we had to select components that contained the lowest mass possible that could meet our related motion requirements, such as position accuracy. In addition to this, a motion subsystem that has a low mass must be selected as to not introduce large forces into a total system, like vibration, undesired motion, motor fatigue, and fatigue stress. So in our case, we chose the CoreXY motion system, This system is driven by using motors and timing belts. The pro to the system that uses the timing belts to lead a system that is precise and minimizes load in the X direction. The use of a single motor creates motion in the 45-degree angle. The combination of both motors creates motion in both the X and Y axis. With the two motors being operated at the same time, the belt configuration provides a stable motion in comparison to two motors that individually can control the two axes. This configuration is especially useful since the Y-axis only carries the extruder and crossbeam, minimizing the weight on the system, creating a motion system that maximizes print speed while maintaining accuracy. This system would also be self-aligning when it comes to the print head, and it only utilizes two motors. The minimization of the motors allows for funds to be allocated elsewhere in other subsystems. It would combine the XY motions into a singular system, which would minimize the amount of error in the movement process. It also doesn't impose any additional mass upon the system, as the two motors placed in the corners of the gantry system. This system is especially user-friendly, as the maintenance for this concept is relatively straightforward, in that the user will simply change out the timing belts as necessary.
It was determined that any custom machine parts for the printer would need to undergo structural finite element analysis. ANSYS Mechanical 2022 R2 was used for this task. Accurate materials were assigned for each part, adaptive meshing was utilized to ensure convergence of the solution, appropriate boundary conditions were carefully applied, as well as consideration for worst-case loading scenarios. After solving, standard von Mises stress and deformation plots were created. The stress and fatigue tools were then used to create safety factor plots, which provided insight on how much margin the parts had. All parts exceeded failure thresholds and were cleared for production. Preliminary thermal analyses were also conducted to better estimate the characteristics of the print chamber. ANSYS Fluent was chosen for this task. A conjugate heat transfer study of the printer was attempted. Standard air and aluminum materials were selected. Inlets and outlets were made in the relevant locations and set to intended real-world values. Thermal boundary conditions were applied to the walls of the printer, as well as the heated print bed itself. The simulation continued until convergence criteria were met and results were plotted.
As you saw from the ANSYS portion of this video, the thermal convection from the printer to the outside air was taken into great consideration for general safety and effect on the components. Heat transfer was decreased as greatly as possible with a multi-layer boundary of fiberglass insulation on the inside and plywood on the outside. According to multiple calculation methods, 1.5-inch insulation proved to be more than enough to keep the heat that exits the chamber at safe levels, and the fiberglass nature makes it fireproof, protecting the user on all fronts. Heat enters the system from the heated fan that was installed on the outside of the chamber and the heated bed that was constructed by the team. The heated bed was created by arranging lengths of 50-foot nickel chromium wires into parallel resistors in a way that was designed to cover the surface area of the print bed most evenly. High-temperature silicone as well as a fiberglass sheet was then used to hold the system of wires in place and attach it to the base plate to complete the heated bed. The final component of the printer is the heated nozzle that was cooled through a water coolant system. Cold water is sent from the chamber through tubes that are rated for high temperatures of the nozzle and into a special chamber in the nozzle that cools it down. Then hot water is pumped back into the fan-cooled radiator that lowers the temperature of the water and makes it usable again. To heat the nozzle, there are two 50-watt heaters installed in the hot end to keep the filament running through smoothly. These 50-watt heaters, as well as other thermal components mentioned, were made possible with electrical wiring and are controlled and observed with thermistors and thermocouples.
The heart of the system is a Duet 3D motor control board with a Raspberry Pi single board computer, power supply by 24 volt, 5 volt switch mode power supplies, and by 75 volt power supply for the main drive motors. These relays are for the emergency stop function. This is the wiring bus for motor signals and power. These breakers control voltage to the power supplies and heaters. The bed and chamber heaters are powered for mains voltage and are switched by these solid state relays here in the center of the case. This is the main power switch. All the component connections are at the bottom and side of the case, including for the main drives, limit switches, cooling system, heaters, etc. All other connections are through these ports here. Main system power is 240 volts, driving two 24-volt DC power supplies at 162 and 100 watts, a 5-volt DC supply at 50 watts, and a linear 75-volt DC supply.
This concludes our presentation on the large format 3D printer. Thank you for watching.